As students, I am really happy that I am going to discuss with you some important problems for university point of view. Today, we are going to see some problems in the first unit as well as in the second unit. In the first unit, we are going to see some problems in the truth table as well as the equivalence formula method, because the students feels that prove the following equivalence by equivalence formula. Without using truth table, you have to use that to prove that the given formula. So I am taking such a type of problems and I am going to discuss. The second problem is that of about the recurrence formula. There also some students are finding difficulties in solving it. So I am taking one linear type of recurrence relation and dissolving them, and another one is a quadratic equation and how to solve that. Thirdly, I am going to take some induction problem. Okay, so the induction problem also very important in the second unit, so you have to clearly understand what the induction problem is, how many steps are involving, how to make to prove the given problem. So these are all that I am going to take. So some 4 or 5 problems includes in this video. So listen carefully and then you will understand. If you are not understanding first time, you repeatedly listen to this video, then only you will understand it very clearly. So repeatedly you have to play this video, then you will understand what I explain to you. So all these topics are very easy, so give importance and Happy New Year. In this new year, I am very happy to present these videos to you to make you understand the concept of mathematics in your discrete mathematics syllabus. Again, a Happy New Year, and let me go to the problem. Okay, thank you. Okay, students, in this class I'm going to talk about what is tautology, and one more question is asked here. Without using truth table, we have to show that the given statement formula is a tautology. That's what we have to. So 2 questions we have to answer. First one is what is tautology. The second one is the given statement formula from here to here is a tautology. That's what we have to answer here. Now, to answer the first question, what is meant by tautology? A statement formula which is true always, irrespective of the truth values of the individual variable, is called the tautology. Okay, so whatever may be the combination of the individual variable, the final result is always true, and that is called tautology. Okay, now take for example here, this is a big formula, so whatever may be the truth combinations of P and Q, the final truth table will give you all true value, the truth value as true, and therefore this statement formula is called tautology. Now let us prove that. Now let us consider let us consider this one, that is negation of negation P and negation Q or negation R. This is what we are taking first now, and that is what we are taking here, negation of negation P and negation Q or negation R. So this is exactly equivalent to, or this implies what is that here, negation of negation P and negation of Q and R. Now look at this particular bracket here. De Morgan's law is used. De Morgan's law is used here. Negation of Q or negation of R would be equal to negation of Q and R, and this exactly equivalent to the first. You look at that here, which implies again we are using the P negation of negation P. We can say P R. I mean, again the negation law is used here. Negation of negation P and negation Q and R. Okay, so here we are using the De Morgan's law again. You will get here negation of negation P or negation of negation Q and R. So that negation will get cancelled. You will get here P R negation and R. So now we are applying the distributive law PRQ, that is PRQ, then this and will come here, then PRR, that is PRR. So now I am taking this as equation number 1. Okay, now consider the other part from here to here of the given equivalence formula. From here to here of the equivalence formula we are taking. That is what I have taken here. Negation of P and negation of Q, or negation of P and negation of R. Again, by using the De Morgan's law here, negation P and negation Q is exactly equal to negation of PRQ. Similarly here, negation P and negation R, by using the De Morgan's law, you will get negation of PRR. So the first step also De Morgan's law is used, and second step also De Morgan's law is used here. Again, look at this, we can use the De Morgan's law, negation of PRQ or negation of PRR. Negation of PRQ or negation of PRR can be written as negation of PRQ and PRR, again by using De Morgan's law. De Morgan's law is used here, negation of PRQ or negation of PRR we can write as negation of PRQ and PRR. Now what I do there, these two values, that is this equivalent formula, this, and for this equivalence formula is this, I am substituting here in this given statement formula. Okay, right, if you substitute that, we'll get PRQ as it is, it would be there, PRQ and PRQ, that is this one, equation number 1, PRQ and PRR are, then this value, that is this value we are substituting, we will get negation PRQ and PRR. Now again what we do here is that PRQ and PRR I am taking here, PRQ I am taking there, or this R I am writing negation of PRQ and PRR. Okay, so this PRQ and PRQ becomes PRQ, and this comes as it is after, and this R comes negation of PRQ and this and PRR. Okay, so look at that, here a tautology comes. So tautology means what? The same formula, or with the negation of the same formula, then tautology we get. Okay, by the rule of tautology, take for example this as A or negation of A, and that would be a tautology. Okay, so the whole bracket comes here also with tautology, with the negation. So an equation or a statement formula, or with the negation of the same statement formula, we will get tautology. Okay, thus the given equivalent statement formula will be equivalent to a tautological statement. So thus we are proving this theorem. Okay, so thank you very much. Okay students, I am really happy to describe or to explain one more problem in the first unit. This is what the problem. It is given that there exists x, p of x and q of x. This left hand side is equal to the right hand side. That's what we have to show here. We have to show that there exists x, p of x and q of x, implies there exists p of x and there exists q of x. That's what we have to prove here. Okay, so suppose this is I am taking as left hand side, LHS I am taking here, and this I am taking as RHS. Now this side RHS. Now you take LHS first, so I am taking LHS first. Okay, and what is LHS given to us is here that there exists x, p of x and q of x. This is what the rule given to us, the premises is given to us. Okay, that's what we have to write here. Second one, we are using existential specification. That means this is, there exists some rule p of x and q of x. So that rule can be applied for a particular element. For a belongs to x, for a belongs to x, we can apply this rule. So in that case, what we'll get? Existential specification. This is existential statement formula. We can specify a particular element a, and we are getting that existential specification on step number 1. We'll get p of a and q of a. Right, now how the step number 3 comes from the tautological rule. Okay, so what the tautological rule says, if p is one statement formula, okay, and q is another statement formula, then that implies we can replace this by p or sometime q or q. So this is one tautological rule is there. So that rule I am applying on step number 2. On step number 2 I am applying here. So p of a and q of a, we can write it as p of a by using this tautological rule. Similarly, by tautological rule on step number 3, on step number 2, we can get q of a also, because p and q is given to us, implies q also we can write. Okay, we can replace the truth value of p and q would be equal to q. That's what that rule we have applied here. Now we are using existential generalization on step number 3. So this is step number 3, p of a. This is specified value. This property or characteristics is satisfied when x equals a. So we can extend this existential generalization. When we generalize this, we will get there exists x, p of x. So we are generalizing this idea, and then we are getting this particular step. Okay, so similarly, if the characteristic is true for a, then you replace the a by x and generalize that to existential. We'll get there exists q of x. So we are replacing a by x and there exists x. Okay, there exists some x for which q of x is true. Okay, so we are generalizing this specified characteristic for some existential variable. So we are getting this one. This is what we say existential generalization on step number 4. We are applying step number 4, the existential generalization, we get step number 6. Now you apply on 5 and 6 the rule, tautological rule. What is the tautological rule? Says if there exists p and if there exists q, and these two can be replaced by p and q. This is what another tautological rule. Okay, so if there exists two statement formula p and q, then we can replace it by p and q. So here there exists p of x, one predicate formula, there exists q of x, another predicate formula. From 5 and 6 we can make this conclusion. Okay, the conclusion comes from this tautological formula, tautological rule. That rule is this: if p and q are any predicate formula, then p and q also exists, and we can replace this 2 by this one. So we are replacing 5 and 6 by step number 7. Okay, and this is what the RHS. Let me catch, this is RHS. So we have started with LHS and we applied some rule. The second step we used existential specification. In the third step we have applied rule T, tautological rule T, that is p and q implies p or q. And in the fourth step also, by using second one, we can get b and q equals q. And these two we can apply existential generalization, because this for a particular property this is true, so we can generalize to the existential factor that exists some x p of x. We are getting step number 5, and for 4 we are getting 6. Then by using tautological rule, if p, q are any two tautological formula, then p and q exists. So we have from 5 and 6 that exists p of x, that exists q of x. We get 7th step as that exists p of x and that exists q of x. Thus we get the RHS. So we have taken the LHS and we proved the RHS. Thank you very much. Thank you, students. This is the next problem I am taking, because this type of problems many times it is asked in the university question. Okay, so that is why I have taken this type of mathematical induction problem. So this term is divisible by 8 for n is greater than or equal to 2. That's what we have to prove here. For n is greater than or equals to 3 power n plus 7 power n minus 2 is divisible by 8. Is divisible by 8. That's what we have to prove by mathematical induction. Now this proposition we are taking as p of n. So p of n equals what is given here, you are writing as it is. 3 to the power n plus 7 to the power n minus 2 is divisible by 8. That's what the proposition we are taking. The first step is that for n is equal to 1, this p of n or p of 1 is satisfied. That's what we have to prove. So in the place of n here, you put 1. You will get 3 to the power 1 plus 7 to the power 1 minus 2. 3 to the power 1 plus 7 to the power 1 minus 2. So 8 is divisible by 8. Let me calculate. 3 plus 7, 10. 10 minus 2, 8. So 8 is divisible by 8. So this is true when n is equal to 1. That is the first step. So if any equation is given to us, you substitute n is equal to 1, the equation should satisfy. So here this term is divisible by 8 when n equals 1. So for n is equal to 1, it is proved. Now we have to assume that the given fact, that is p of n equals 3 power n plus 7 power n minus 2, is divisible by 8, and that is true for some number k. For n is equal to k, we are assuming that the given equation is satisfied. The given equation is this, given proposition is this, that is satisfied for n is equal to k. That is what the second step. Now our aim is that we have to prove that p k plus 1 is true. If we prove that p k plus 1 is true, then the totality, the induction proof is over, because for n is equal to 1 we have proved already. If n is equal to k plus 1 is true for some k greater than or equal to 1, then for 1 it is true. For 1 k is equal to 1 you take, then n is equal to 2 it is true. Then n is equal to 2 it is true. Then put here k is equal to 2, then 2 plus 1 3 true, then 3 plus 1 4 true, then 4 plus 1 5 true. Everything's are true. Am I right? So first we have proved that n is equal to 1. We assume that n is equal to k in this step. Now we have to prove that for k plus 1 it is true, right? The given equation, given proposition, you substitute n is equal to k plus 1, then you will get p k plus 1 equals 3k plus 1 plus 7k plus 1 minus 2. This how can we write? This 3k plus 1 we can write as 3 into 3k plus this 7k plus 1 we can write as 7 into 7k minus 2, and this we can write it as 3 into 3 power k, 3 into 7 power k plus 4 into 7 plus k. That minus 2 we can write as minus 2 plus 4. Here 7 into 7 power k can be written like this. Okay, why? If you write the short form, you'll get 3 plus 4 into 7 power k. So this is what is exactly equal to this. Okay, therefore this 7 into 7 power k we can write it as 3 into 7 power k plus 4 into 7 power k. This minus 2 we are writing minus 6 plus 2. Now rearrange this, we can write like this. This step you rearrange, you will get this step. Why we are writing like this? Because we have to show that these two terms are divisible by 8. That's what we have to prove. That's why we are writing this form into this form. Now you take the first step, first factor, first term in this step. The first term is this. Okay, this is divisible by 8 because Look at that. The first step, 3 power n plus 3 power k, otherwise this is equation number 1. From equation number 1 what you get is that it is divisible by 8, we have assumed. Therefore 3 into divisible by 8, definitely it is divisible by 8. Now come to the second term here. This is what the second term, okay. This second term, is this divisible by 8 for different k? Yes. For 7th power 1 plus 1, 8, divisible by 8 even if it's multiplied by 4. 7 power 2, 49. 49 plus 1, 50. 50 into 4 is divisible by 8. Yes, 8 divisible by 8. I'm right. So if k is equal to 2, 3, 4, whatever it may be, if you add with this one, multiply by 4, this term is divisible by 8. So this term is divisible by 8 plus this term is divisible by 8. Therefore the sum of the two divisible by 8 is again divisible by 8. Am I correct? So p of k plus 1, we can write it as 3 into 3 power k plus 2 power 7 power k minus 2 plus 4 into 7 power k plus 1 is divisible by 8 is true. So we have proved that for n is equal to 1 it is true, for n is equal to k it is true, and then for n is equal to k plus 1 also it is true. That is, the bracket is divisible by 8. Okay, so now by mathematical induction method, this fact, divisible by 8 by 1 is true, and thus we can prove any mathematical induction problem. First we have to prove that for n is equal to 1 it is true, and afterwards we have to assume that for n is equal to k it is true, and from that assumption we try to prove that for n is equal to k plus 1 is also it is true, and therefore for n is equal to 1 it's true, for k plus 1, for k is greater than or equal to 1 is true. Therefore for n is equal to 1 it is true, for n is equal to 2 it is true, for n is equal to 3 it is true, n is equal to 4 it is true. Therefore for all n greater than or equal to 1, this particular concept in mathematics is true. That way we can prove this induction method. Okay, so we can see another problem in another video. Thank you. Okay, welcome students. In this class I'm going to take another problem. Okay, in this particular problem I'm going to solve the recurrence equation by factor method. Another method is also available, that's called generating function method. So first let us talk about the factorization method to solve the recurrence equation. That's what the first one we are going to see now. Okay, so let me take you to that problem here. This is what the problem. Find the associated homogeneous solution for this. Okay, so homogeneous equation is of the form, this is called homogeneous equation. an equals 3an minus 1 plus 2n. So in such an equation you have to consider only this a suffix n and a suffix n minus 1. These terms should not to take into account. So now you bring these terms this side, what we'll get is this, semi-correct. So an minus 3 an minus 1 equals 0. Now you replace this an by r and minus 3 into this an minus 1 by a constant, or we can say 1 This is 1. Okay, so for an you are writing r. For an minus 1, it's a constant, that's 1, so that equals 0. Now from this we know that r equals 3. R equals 3 there. Now the solution of this particular equation, homogeneous equation, would be equal to an equals some constant alpha into the root to the power n, 2 to the power n. That's what the general form of the linear equations. Okay, so here we can write as, and here the root is what? R. So how can we write? an equals alpha, some constant, into what is 3, and that is what the root, 3 to the power n. And this is what the solution of the given linear equation. This is the way we have to solve the linear equations. Okay, so in another video I will teach you about how to solve the quadratic equation. Here this is a quadratic equation. How to solve this I will teach in the next video. Okay, so till then I have to say a goodbye to you. The next class I'll see you with another problem. Thank you. Okay students, in this class we are going to discuss about how to solve the recurrence relation by using factorization method. That is what we are going to use now. Now let me take the problem now. This is what the problem. This one, you take this one. Solve sk minus 7 sk minus 1 plus 10 sk minus 2 equals 0. So this type of question we call it as recurrence relation. Okay, so recurrence relation, that's what we have to understand. This is called recurrence equation. How to solve this? Solve means to find the solution of this. Solution means from which we have to get the recurrence format we have to get. That is what we say, it is a recurrence, solving recurrence equation. Now the first step is you write the given recurrence relation or equation as it is. The second step is that in the place of sk you replace by r squared. Okay, then you write the coefficient of sk minus 1 like this. In the place of sk minus 1 you are writing r. Then you are writing the next coefficient as 10, and in the place of sk minus 2 you are putting as 1. Sk minus 2 is equal to 1, then equals 0. So you understand that if the equation is given like that, what we have to write? In the place of sk you replace by r square. In the place of sk minus 1 you are writing r. In the place of sk minus 2 you are writing 1. So the given relation can be written as r square minus 7r plus 10 equals 0. Now we are solving this quadratic equation. If you solve this quadratic equation, then we have to write 10 here, If you multiply the two values, you have to get 10. If you add the two values, you have to get minus 7. Am I correct? If you multiply the two numbers, you have to get 10, and if you add two of them, you have to get minus 7. The chances are minus 2 and minus 5. Okay, so these two are the factors here. So we can write this quadratic equation in the factorization form like this: r minus 2 into r minus 5 equals 0. From this, the two roots are r equals 2 comma 5. The two roots are what? R equals 2 comma 5. So we have solved the characteristic equation and we got this root. Okay, now you must know the general form of quadratic equation, or general solution form of quadratic equation. This is the general solution of quadratic equational form. Sk equals a some constant into the first root. Here the first root is what? 2. So that 2 you have to write here, 2 to the power k, plus another constant into the second root here to the power k. So the final solution is Sk equals constant a into first root to the power n plus b into second root to the power n. So n we can write here, and here also we have to write n. So Sn equals a into 2 to the power n plus b into 5 to the power n. This is the general solution of the recurrence relation given to us, that is Sk minus 7 into Sk minus 1 plus 10 into S into k minus 2 equals 0. So this is a way we can solve the recursion equation whose characteristic equation is a quadratic equation. So with that we have to come to the end of this problem. Okay, so I will come with another problem in the next day. Okay, so thank you.